In this class, we discuss the solution of one-dimensional wave equation by canonical reduction, or it is said that the solution of one-dimensional wave equation by reducing it to canonical form. Okay, so we first let the one-dimensional wave equation, and this is given by del 2u by del t2. This is equal to c square into del 2u by del h2, where c, this parameter c, is said to be velocity of the wave. Okay, and x is in minus infinity to infinity, that is for all x belongs to r and t greater than 0. And we name this relation or this given equation as the equation number 1. Now we first compare the equation number 1 with the general partial differential equation of second order, and which is of the form a into del 2u by del t2 plus b into del 2u by del x del t plus c into del 2u by del x2 plus f of a function of x, t, u, del u del t, del u del x, this is equal to 0. And comparing this relation with the relation 1, clearly it is shown that a this is equal to 1 because here 1 present, and we get b, this is equal to 0 because there is no term of del 2u by del x del t, and capital C, this is capital C, is equal to minus c square because c square del 2u by del x2 present in the right side, and obviously f, this is equal to 0. Now we find the discriminant of the equation 1. What is the discriminant? Discriminant is denoted by capital D, and this is nothing but b square minus 4ac, and clearly by putting the value of b, a and c, the discriminant is 4c square. Okay, and 4c square obviously greater than 0 because c not equal to 0. So from this relation, since the discriminant is greater than 0, so we say that the wave equation in one dimension must be hyperbolic PDE, right? And this is for all x t belongs r, 0 to infinity. R because this, and 0 to infinity because this. Okay. Now we find lambda quadratic equation. What is lambda quadratic equation? By using the value of a, b, c and using the variable lambda, for the name lambda, this is said to be lambda quadratic equation. We get the lambda quadratic equation as a lambda square plus b lambda plus c, this is equal to 0. This is the working rule to find the canonical form of hyperbolic equation. We already discussed in previous class. Okay. Now we put the value of a, b, c, we get lambda square minus c square, this is equal to 0, and so the equation gives two value of lambda which are plus minus c, and hence we find the characteristic equation or two characteristic equation. The first is dx dt plus c, and the second is dx dt minus c, this is equal to 0. And solving the ordinary differential equation, both of them, we get x plus ct, this is equal to a constant, arbitrary constant c1, and x minus ct, this is equal to another arbitrary constant c2, and these are said to be the characteristic of the wave equation 1. Okay, these two are the characteristic, this and this and this are the characteristic of the equation 1. Now from the characteristic, other than the arbitrary constant, we assume here another two variable. The first is xi and the second is eta. Here we introduce the variable xi equal to x plus ct and eta equal to x minus ct. Now we differentiate xi and eta with respect to x, t, xx, xt and tt. Okay, and get the value xix. These are the partial derivative with respect to x. These are the partial derivative with respect to t, and so on. We get for xi and for eta similar. Okay. Now we know that we have to find another four quantity here to reduce its canonical form. Four quantities are small a, small b, small c. Small a, small b, small c, and 8 and 5. Sorry, 4, not 4. This 5 quantity we have to find here. And the formula to find this 5 quantity of canonical reduction are given by small a, this is equal to a into xix square plus b into xy plus c into xy eta square. Putting the value of xix, this is xy and this is xy. Putting the value of xix, xy, from here we get the value 0. And similarly for the value c, this is small c, and we get this is also eta t. Okay, we get also this value is 0. And now we find the value of b. B is given by minus d by a. What is d? D already we find here, minus 4c square by a. A means, a not small a, this is capital A. A means 1. Okay, so we get this is minus 4c square. And the value of f, small f, is given by, here is a mistake, this is not y, this is t, this is also tt, and this is t, this is tt. Okay, and by putting the value of all the partial derivative, and here we put the value of f is 0, we get this is 0. Now the value of phi, this is equal to f by b. Here f is 0, so f by b is obviously 0. Now from this phi result, we can write the canonical form. Canonical form of 1 is given by u, or we write here del u by del xi del eta. This is equal to phi, right? And obviously this is 0. Now from this relation we get another relation by integrating with respect to xi first. This is given by del u by del eta. This is equal to, since we integrate with respect to xi, so arbitrary constant we take a function of eta. Let it be g1. Okay, this is the function of eta. Since here we take eta as constant. Okay, now we again integrate with respect to eta and get the value of u xi eta. This is given by integration g1 eta d eta plus g2 xi, because here we take xi as a constant. Okay, and since this integration is a function of eta and integration with respect to eta also, so this must be a function of eta. Now we take, this is another function psi1 eta, and this is named as another function psi2 xi. We changing the name, let this be psi2 and this be psi1. Okay, so our general solution is u xi eta. This is given by psi1 xi plus psi2 eta. Okay, and since we take here psi is the function of xt and eta is the function of xt, so we write u, this is function of xt and this is given by psi 1 of, we putting the value of xi, this is equal to x plus ct and this is psi 2 x minus ct. So this is the general solution of one-dimensional wave equation by reducing it to canonical form. And here this is the canonical form, right? This is the canonical form of one-dimensional wave equation. Now if we draw a rough picture of t-axis and x-axis and we consider a fixed point on t-axis and this is named as t0, okay, or we take any fixed time t0 greater than 0. Then if we take this point as c t0, 0, then we draw the two lines. The first line is x plus ct, this is equal to c t0, and x minus ct, this is equal to c t0 through the same point ct0, 0. Okay, and clearly this line looks like this, and this is the line x equal to ct plus ct0, and this line looks like this. This is x equal to minus ct plus ct0. Okay, and here the slope of this line and slope of this line is slope, this is equal to c, and slope, this is equal to minus c. For this reason we sometimes call this is the wave in forward direction. Okay, this is the forward wave. And this wave is said to be backward wave. Okay, and these two waves move forward and backward in the same velocity, because c is the velocity of the wave we say in the first line. Okay, so this is the forward wave with the velocity c, and this is the backward wave with the velocity also c. And we say that the general solution of one-dimensional wave equation is always the sum of two waves, one forward and one backward, but both have the same velocity. Okay, these are the total concept of solution of one-dimensional wave equation by reducing it canonical form. Thank you for watching.